for chapter 31. We're going to do problem 21, 23, and 29. I believe somebody asked about 31, but 31 wasn't assigned. So you don't have to know 31. So if you want to know how to do it, come to my office. Otherwise, who cares? So number 21, we were given this wire, long straight wire that has some current flowing through it. And we were given this wire loop that's next to it. We're told this wire loop is a distance d away, that it has a width of w and a height of h. They also tell us that the current in this wire is, 2.5 amps, if I can read my handwriting. Wonderful. Thank you very much, Odie. Okay, so then we're also given a hint. We're given a hint and told we need to find the electromagnetic flux, which is this Greek letter phi. And we're told to use equation 31.4 to sum flux in loops. And we're also told that dA is equal to H times dr. Okay. So how would we go about solving this? What should be the first thing you would do when you see this problem? Shut the book and throw it at something? Say that?
The unknown.
Knowns and unknowns and that kind of stuff. They give us some variables. What variables do they give us? They gave us I. What else did they give us? They gave us that the width is, 0.3 meters. Thank you. Did they give us the D? D is 0.1. And did they give us the height? Height is 0.5. Anything else they gave us? So we got to make sure that we write down everything that they gave us. They gave us one more thing. They gave us to use equation 31.4. So what would be a good idea? Write down equation 31.4. What is equation 31.4? If you don't remember, you can go to the chapter summary and you can actually look. Equation 31.4, it says that it's called magnetic flux, which might be an important thing to know for the chapter about magnetic flux. This is kind of a key equation. Magnetic flux is equal to the integral of B dot dA. Magnetic field multiplied by the differential area of that magnetic field. Is there anything I can plug in? dA. What is dA? HDR. So phi is equal to the integral of B times H dr. What does HDR actually mean? What does dA mean in general? Change in area. And what is the area of this loop? Square. So if I were to just multiply it to get the area out, what would the area be? W times H, the width times H. Yeah? But I need to integrate over this area. I need to integrate over the whole thing. So H is still the height, but I need to integrate that height over dr. Dr is the distance you are from the wire, because the wire is creating a magnetic field that's going to cause induction to happen. Anytime you have a magnetic changing current, it creates a magnetic field. That magnetic field creates current flowing through that. That's the whole idea of induction. So we're going to create a magnetic field here because of this wire. How do I find that magnetic field? What kind of wire is this? Just a long straight wire. What's the magnetic field of a long straight wire? All this shit stacks on itself. B of a long straight wire is mu naught times I divided by 2 pi r. Yeah. Magnetic field due to a long straight wire. Put it on note card, memorize it. So mu naught, do we know mu naught? Yeah, it's constant. 4 pi times 10 to the negative 7. Do we know what I is? Do we know the current? Yeah. Yes, divided by 2 times pi times r, where r is the distance you are from the wire. Now, this is my current. What's my distance of this loop from the wire? Is it only one distance? This side is d. How far is this side? D plus w. So I have to integrate over that whole distance. That's where that dr comes in. I'm adding up all the contributions from distance d all the way to distance d plus w. So I can take this magnetic field due to a long straight wire and I can plug it in here. So I'm going to plug that equation in. Phi is equal to the integral of mu naught times I over 2 pi r times h dr. What were the limits? What's the closest distance from the wire I can be? D. What's the farthest distance? D plus w. Can I pull anything out of the integral? Almost all of it. Everything except for anything that has a r. So phi is now equal to mu naught, comes out, I comes out, h comes out, over 2 pi times the integral from d to d plus w of 1 over r times dr. Phi is mu naught I times h over 2 pi. What is the integral of 1 over r with respect to r? Francis back there mumbling. Do we have an answer?
Right here.
Natural log. Natural log of d plus w minus the natural log of d. The integral of 1 over a variable, 1 over r, is ln of r. So I take ln of r, plug in my limits, plug in my final, d plus w minus my initial ln of d. We have numbers for all these things, don't we? Yeah, so you plug in all of your numbers, and once you plug in all your numbers, you'll get an answer of 3.5 times 10 to the negative 7. I should not waste your time with plugging numbers into calculators. So that's the approach. Phi is 3.5 times 10 to the negative 7, comes from doing that integral. Mu naught is 4 pi times 10 to the negative 7. It's constant. It's on your equation sheets that I handed out. As is the integral of 1 over x dx. So you have that general integral on your equation sheets too. Okay. Any questions on that one? What are the units of magnetic flux? Flux is the integral of B dot dA. So what are the units of B? T, which stands for Tesla. And what are the units of area? Meters squared. Tesla times meters squared. That is our flux. Okay? Questions on that one? All right, let's do number 23. And number 23, I have a demonstration that I'm going to walk around and actually show you at your tables too, so you can get a better idea of it. In 23, we have a current in a long solenoid of radius 3 centimeters. So big radius is 3 centimeters. What should I usually immediately do with that number? Convert it to what? How many meters is that? 1.03 meters. Perfect. And that current in the solenoid is increasing uniformly at a rate of 1.5 amps per second. What is that? Amps per second. What do amps measure? Current. And per second, what is current? What is per second? Time. So this is a change in a current over a change in time, di dt. 1.5 amps per second. The solenoid has 350 turns per meter. N over L is 350 turns over meters. They ask us, what is the induced electric field, a distance little r from the solenoid axis, when A, r equals 2 centimeters, and B, r equals 4 centimeters. So first of all, what is a solenoid? Anybody? Solenoid. What is a solenoid? It's what? A loop wire. This is a solenoid. A bunch of wire just wrapped into a coil. What is this? Slinky, also a solenoid. Bunch of wire wrapped into a coil. Okay? So this is what we're working with. And we're going to take current and we're going to move it through this. When we make current move through this, that creates a magnetic field. Just running electricity through some kind of coil turns a magnetic field on. And you'll see in a demonstration that I'll walk around to your tables to show you that we make the exact middle of this has a magnetic field. So we're inducing a magnetic field in the middle of this just by running current through it. And that's what this is talking about. Size of the magnetic field depends on some variables. So we need to first figure out what is the electric field that we're inducing in this. To do that requires a few steps. So we have an equation for inducing an electric field from EMF. EMF is induced voltage is equal to an induced electric field times 2 times pi times r for a solenoid. Good general equation to keep in mind. We also have another equation for induced EMF is negative d phi dt, the change in magnetic flux. So if I can take these two equations, I can solve for them, I can set them equal to each other, and I can find what my E is. That's going to be our procedure for solving the problem. So let's go to this EMF equation, negative d dt of phi. What is the equation for phi? What is magnetic flux? Integral of b dot dA. If we have stuff set up that's varying as our distance changes, we don't have that here, so we can simplify it. We don't need to worry about integrals. We can just do b times a. Since we're not given a spread out kind of shape, we're not varying our distance away from this solenoid, we can just use b times a. That's magnetic flux. Okay. So we have b times a. I need to take the derivative of that. How do I take the derivative of b times the derivative of a? First times derivative of the second, so this is negative b times dA dt plus the second times the derivative of the first, a times dB dt. In this particular problem, this goes to 0. Why? This is my solenoid. What would dA do? What is dA? Change in area. Do they say anything about changing the size of this solenoid in the problem? So is this size changing at all? If it's not changing, what's the derivative of it? 0. Derivative is a change. If it's not changing, it's 0. So dA dt goes away. Now B is the magnetic field changing. We have to figure that out. So to do that, we have to figure out what is the magnetic field of a solenoid. Magnetic field of a solenoid. I will have a heart attack if somebody knows this equation. Anybody know this equation? No? You just want to save my life, that's all. Is mu naught times n divided by big L times I. Yeah. It's all in chapter 31. How many of you have read chapter 31? How many have watched chapter 31? How many have done the homeworks for chapter 31? Okay. It's showing. Okay, so EMF is equal to negative A, which would be the area. What would the area be of the solenoid? What's the area of this thing? What kind of shape is it? Let's use this one. Cylinder, so what's the area? You said it. Pi r squared. So we can plug in pi r squared for our area. Let's do that. And then we need to take the derivative with respect to time of mu naught times n divided by L times I. Oh, geez. This derivative looks like it'll be a pain in the ass. I gotta take the derivative of how many different variables are there? It's like 4 different things. Mu naught, n, L, and I. This is derivative with respect to time. Mu naught, what is mu naught? It's constant, doesn't change. No, so we don't have to do that, we can pull that out. How about n divided by L, the number of turns that I have per length in the side of this coil? If this is my coil, is the number of turns that this coil has changing? No, so is n over L changing? No, so it gets pulled out. So we now have negative pi times r squared times mu naught times n divided by L times di dt. Okay, well that still seems kind of shitty. We got to figure out what di dt is. We know what it is? What is it? They gave it to us. What is it? 1.5 amps over seconds. How about n over L? Did they give us that?
Yes.
Yes. What is it? 350 turns per millimeter. Mu naught. What is that?
4 pi times 10.
4 pi times 10 to the negative 7. Pi r squared.
R.
They gave us an r. So they gave us all these variables. At this point, I can just plug and chug. But I'm not going to quite do that, because I need to take this EMF, set it equal to this EMF, because I'm looking for what E is. General equation for the induced electric field. Set those equal to each other. E times 2 pi r equals negative pi times r squared times mu naught times n over L times di over dt. What happens to my pi's? I have a pi on the left and a pi on the right. I eat both of them so I can bike 50 miles. They're gone. What happens to my r? One of the r's cancels, and I end up with just one r. So now my E becomes negative r times mu naught times n divided by L times di dt divided by 2. At this point, you can plug your numbers in. So in part A, you're asked to find what is this induced electric field if R is less than, if R is equal to 0.02. So we're told we have this cylinder, yep, this solenoid, and we're told that the total radius of this solenoid is 0.3, and we're going to find what is the electric field induced at 0.2. So we're inside of this solenoid. We're in this middle area. So we have to find what is the induced electric field. So we plug in 0.2. So just plug in your 0.02 times mu naught over 2, your n over L, which was, oh gosh, 350, and your di dt is 1.5.
plug those numbers in. E is equal to 6.6 times 10 to the negative 6. Now here's the tricky part. Part B asks you, what is the induced electric field if R is equal to 0.04? How big was the solenoid? 0.03. If I'm 0.04, then I'm on the outside. Turns out when you induce magnetic fields in solenoids, on the outside, the total magnetic field is 0. So anything between the outer edge of the solenoid and any radius that's bigger than that contributes nothing. So instead of plugging in 0.04, I'm going to plug in R equals 0.03. Because it'll only have a magnetic field based on the maximum size of your solenoid. There's going to be no magnetic field created outside. You will see this in the demonstration that I'll do at your table. So that's why we plug in 0.03 instead of 0.04. Plug in your R equals 0.03, and you'll find that E is equal to 7.4 times 10 to the negative 6 volts per meter. Where you're going to run into big coils of wire, big coils that create magnetic fields in your chosen careers. You're all going to be doctors. Where do you have these? MRI. MRI is a giant one of these. What if you have a really fat patient? What do you do with them? They don't fit inside the MRI. What do you do?
Don't not become a doctor is what you do.
What did you say you did?
I'm kidding.
I didn't hear it. What was it?
You get a bigger
Get a bigger MRI?
Yeah.
Actually, that's exactly what you do. You send them to the zoo.
Yeah.
And then they feel horrible because they have to take an elephant MRI.
Are you serious?
Yeah, that's actually what they do. Yeah. Don't do that.
Can we wait? No, it's okay. Where are you going?
Okay.
That's weird.
So this stuff, you might not like it, but it's relevant. You're going to be using the technology. You might not understand it, but you'll be using it. Next question, last problem that we're going to do number 29. So number 29, I have a rectangular loop that I'm pushing into a magnetic field. So 29 looks like this. I have a magnetic field. These X's represent the magnetic field. What direction is this magnetic field going if I'm drawing X's? Into the paper, into the board. Is that positive K, negative K, I, J, what is it? Negative K. So this magnetic field is going in the negative K direction. Okay? And we've got a rectangular loop that we're shoving into this. The rectangular loop has a width of 80 centimeters and a height of 20 centimeters. They tell us this is made out of heavy copper wire that has a radius of 0.13 meters, 0.13 centimeters. And we're taking this loop and we're shoving it in, short side first, at a speed. So we have a velocity here of 0.4 meters per second. And the magnetic field has a strength of 5 times 10 to the negative 2. We are asked in this one to find what current we're inducing inside of this loop. So we're taking a loop, we're shoving it into a magnetic field, so we're establishing a changing magnetic field. Anytime there's a change in a magnetic field, there's going to be induction. There's going to be an induced magnetic field. If I'm shoving this thing in, that means I'm increasing the magnetic field that's going into the board. Yeah? Now there's something that happens with induction with Lenz's law. What does Lenz's law say? We should get this from the video. Just conceptually, Lenz's law, what does it say? Does Lenz's law like change? No. It wants shit to stay the same. It doesn't like anything changing. So if I'm shoving this thing in, I'm getting more x's inside of this loop. Right? As I push these things forward, I go from 2 x's. If I come back a little bit later, there's going to be 3 x's inside of this loop. Yeah? Is Lenz's law happy about that? No. How many x's does it want? It wants just 2. So how does it get just 2? Gets rid of one of the x's. How do you get rid of an x? You ghost them. How do you get rid of an x?
Changes the direction.
Changes the direction. So we're going to induce a magnetic field. That'll be the opposite direction. So this blue line, that's the induced magnetic field. There's going to be current that moves around in this loop that's going to create a magnetic field that's going to go out. We're going to do a practice problem that talks about all of this. Okay? So that's what's going on here. We're inducing a magnetic field. That direction for that induction is going to be counterclockwise. Give me that direction that I want. This is where the second right-hand rule comes into play. If I take my thumb, put it in the direction of the current that's induced, it's going to the left, down on the bottom. I take my fingers, I point them to the place where I want the magnetic field. I want the magnetic field above this wire, and I bend my fingers coming out. So I'm getting my magnetic field coming out. Okay? For the second right-hand rule, you can't use the little demo things that are on your tables. Okay, so that's the physics of what's actually happening. Now the math. What do I actually do to figure this out? Induced current is equal to induced electric field divided by resistance. Where does that come from? I equals EMF over R. Whose equation is that? It's Ohm's law. We are asleep today. Okay. First, I need to figure out the resistance. Resistance of this wire is rho times L divided by A. Rho is 1.7 times 10 to the negative 8. That's for copper. That comes from a table. Copper's resistivity. L is the whole length around this loop. What is the length around this loop? You can think of it like the perimeter. 200 centimeters, which is 2 meters. Yep. So that's why we plug in 2 meters for the length. Divided by the area. Now the area is the cross-sectional area of this wire. So what shape is a wire? What's the cross-section of a wire? This could be a very thick wire. What's the cross-section of this? Circle. What's the area of a circle? Pi times r squared. So pi times 0.0013 squared. Plug in all these numbers, you get your resistance. 6.4 times 10 to the negative 3. What are the units? Ohms. Now I need to find EMF. How do I find EMF? Use Faraday's law. Negative d phi dt. What is phi? B times A. Phi stands for flux. Maybe it'll help. Flux is badass. BA. No. A lot of physics classes, that's the only kind of jokes you get. Okay, so I gotta do the product rule. What do I get from the product rule? First, B times the derivative of the second plus the second times derivative of the first. Here's where this one gets a little tricky. The magnetic field. What do they tell us about the magnetic field? They told us that we're being pushed into a magnetic field, that B is equal to 5 times 10 to the negative 2. Is that changing? No. So what's dB dt? 0. So here, the dBt goes away. I said that really fast. That sounded funky. The dBdt. Here. Now I've got negative B times dA dt. Now dA dt is the area that's actually exposed to this magnetic field. Is that changing? I'm pushing this loop in, so that's what's changing. So EMF is now equal to negative B times d dt of the area. What is the area of this loop? What's the area of a rectangle? Length times width, or let's do length times height, because we've got it drawn a little differently, but same thing, length times height. Yeah. Now I got to take these derivatives. EMF, negative B. Without any thinking at all, we just do the product rule. First times dH dt, derivative of the second, plus the second times derivative of the first. I go up and I look at my little loop. I got to do dL dt and dH dt. dL dt is the length that's inside of this changing as I'm pushing it through? So as I'm pushing this in, this 80, I'm getting more and more of this is actually going into the magnetic field. So that's changing. How about the height? Is that changing? No. So what's dH dt? 0. We get rid of that shit. Cancel it out. So dH dt goes away. So the EMF is now negative B times H times dL dt. dL dt, that's a change in position over a change in time. What is that from physics 1? Velocity. EMF is negative B times H times V. So EMF is negative B, which is 5 times 10 to the negative 2, times H, which is 0.2, times V, which is 0.4, to find that the EMF is 4 times 10 to the negative 3. And the induced current is E over R. So plug those numbers in. .63 amps. Negative should be in there. Okay. Leave it to France to be negative. We are comatose today. Questions on this one? Yeah.
Yeah, I missed how you went from the negative HDL over T to
From here to here?
Yeah.
dL dt, that's the length that's inside of this, and the change in the length divided by the change in time. Change in position over change in time is velocity. Yeah. Anything else? No. All right, let's do one more example that's not in your book. So this is the only place you're going to get it. You don't have a problem to work out for it or anything like that. I'm going to take a region
and I'm going to create a magnetic field inside of this region. It's going to be a uniform magnetic field. And then I'm going to take a bunch of loops. I'm going to take these loops and I'm going to drag them around. I'm going to drag them through. I'm going to label these positions. I'm going to label A, I'm going to label B, I'm going to label C, D, and E. So I'm taking basically a slinky and I'm pulling it through a magnetic field. And I want to know what's going to happen in terms of induction. So induction means that when you change the magnetic field, you induce some kind of magnetic field inside of your object. That induced magnetic field comes from some current that's going to flow that's going to create that magnetic field to resist change, according to Lenz's law. So if I'm at position A, if I've got this coil at position A, if I imagine just a little bit before and a little bit after, is the magnetic field that A is inside of changing at all? A little bit back this way and a little bit over here, is B changing? Nothing's happening to B. So is induction going to happen? So does anything happen at A?
No.
No. So do we care about A? No, nothing happens. We don't have to worry about A. Nothing happens. Let's skip B for now. Let's look at C. If I look at C, how many magnetic field lines do I have going into the board in C right now? One. If I go back a little bit, how many lines would I have? Still just one. If I go over a little bit, still just one. The magnetic field's not changing inside of C. So is there going to be any induction in C? No. Let's look at E. If I go a little bit before, any magnetic field? Go a little bit after? No. Nothing's happening? Any induction there? No. Nothing happening in A, C, or E. No induction at all. We don't care. Induction only happens when you have a change. Now if I look at B. If I look at B, if I go a little bit before I'm inside of this magnetic field, if this loop is out here, how many magnetic fields are inside? There's none. And then I pull it into here, how many magnetic fields are there? There's one. Is this happy about that?
No.
No. What does it want? It wants no change. So how many lines does it want? 0. How is it going to get 0 lines? It has 0 out here. It goes to having a line. It wants to cancel that line out. So it's going to create a line coming out to resist the change, to go back to the way things were. Lenz's law is your racist uncle. Wants to go back to open. Man, even bad taste jokes don't work. Still sleeping. It's on YouTube. It's going to get torn down. Okay, so I create a magnetic field that's coming out of the board to resist the change. I'm not happy about that change. Lenz's law. That's what that negative sign is all about. I resist any change that happens. Now, what direction is the current inside of this loop going to go to create that magnetic field? I could have current going clockwise, or I could have it going counterclockwise. What do you think? Take a guess. I don't care what you guess.
Counter.
Counterclockwise? Let's see if we're right. So if I assume I'm going counterclockwise, where do you want to draw the current? On the top of the loop, left side, right side, bottom? Doesn't matter. Top. Top of the loop going counterclockwise, that would be this way, yes?
Yep.
Okay, so I take my thumb and I point it in the direction that that current's going. Going counterclockwise, going this way. Then I take my fingers and I have to rotate my arm around so that they are actually pointing to the place relative to where that current is drawn, to where I want the magnetic field. I want the magnetic field underneath, right? I bend my fingers. What direction are my fingers going? Out. Is that what I wanted? Yes. So did I choose the right answer?
Yes.
Yeah. If I would have gotten the wrong answer, what would that mean?
Switch that.
Just flip it. Okay? So this induced current at B, we'll do I induced is counterclockwise, and B induced What direction is the induced magnetic field? Out of the board, positive K. Now let's look at D. At position D, I'm inside of this magnetic field and I'm happy with it. And then if I go a little bit outside, what happens to the magnetic field? It goes away. Is it happy about that? No. So what kind of magnetic field is it going to create? It's going from having magnetic field into the board to having no magnetic field. It wants to have the magnetic field into the board again. So how does it do that? It creates a magnetic field going in. So I'm going to induce a magnetic field going in. What direction is the current going to go to create that? Clockwise or counterclockwise? Clockwise? Why do we say clockwise? Because it's going the opposite way, so it's the opposite answer. Okay, so we want to go clockwise. Does that work? Look at the right-hand rule. Take my thumb, put it in the direction the current's going. I drew it on the bottom of the loop this time, going to the left. I want it inside of the loop. If I go inside of the loop, I point my fingers up to be inside of the loop. I bend my fingers, they're going into the board. That's exactly what I want. So I induced is clockwise. B induced is negative K hat. That's an excellent conceptual example. I could give you that on an exam. How many points would that be worth? On this exam. That could be a 10-point question, I think. Why it's going into the board? So here, if I go a little bit before I'm starting to pull it out, I have magnetic fields going in. If I get outside of this loop, I have no more magnetic fields. And it's not happy about that. It wants to go back to when it had a magnetic field going into the board. So it creates a magnetic field going into the board.
Oh, because
On the other side, if I go a little bit before, I had no magnetic field. I want to have no magnetic field. And then I get in here, and I have a magnetic field. I want to get rid of it. It has very bad memory. It doesn't remember any of the stuff that happened previously. It's just immediately before and immediately after.
and that's because you're pulling it down.
Because I'm pulling it that way. If I was pulling it the opposite way, it wouldn't change. If I was pulling it up or pulling it down or diagonally, I'm pulling it from the left to the right, as the alphabet goes. Point A, B, C, D, E, sequentially. We all know the ABCs, yeah? Can we recite the ABCs? A, B, C, D, U, F, G.
Oh no.
Oui. Parlez-vous français?
Yeah, that's it.
Any questions on this? Nope.
CC.
So we have a